Okay, sure. Thank you very much. So, well, good morning from another perspective to all of you. As you can see, I am from Warsaw University of Life Sciences, and the title of my presentation, which is probably longer than the presentation itself, is Insights into Neural Architectures for Learning Numerical Concepts from Simple Visual Data. The outline of the presentation is very short and very straightforward, so we can skip it, and in order to save time, we can go to the main part, to the actual presentation. So I'll start from introduction and motivation, or more precisely from motivation, which is very simple. I mean, we know that basic counting skills for children, for example, develop from experiences, from from visual experiences, and it happens not only for humans, it happens for animals and even for some invertebrates. In other words, it presumably means that the neural mechanisms which are behind those basic numerical counting skills are not very complicated, and neurophysiologists investigate that. But from the AI perspective, it's just an interesting case study, whether it is possible to convert physical, visual data into abstract numerical concepts, into understanding the ideas of numbers or certain numerical properties. And this is the focus of my presentation, even though originally the focus was more on detecting objects in visual data in order to count them. So because I'm focusing on learning numerical abstractions rather than on processing visual data, the visual data are, like in many other recent works in this area, rather straightforward, rather simple, actually binary or nearly binary. And as expected, the proposed machine learning tools are also quite typical neural network architectures, both fully connected and convolutional. The assumptions for this work are further simplifying the problem. First of all, I'm considering only a small range of integers, not exceeding 6, just because this is the maximum number of objects a human can count or can perceive visually without explicit counting. And of course, the images are binary or near binary, black or white, with objects with dots of opposite polarity. And the concepts, numerical concepts I'm interested in is not only simple enumeration from 1 to 6, but also more sophisticated, more advanced concepts which can be created within such a small range. For example, even versus odd numbers, medium, small, large, and other decompositions of this small range of integers into subcategories. Some of them are, of course, quite artificial. And two main problems, two main issues are whether such concepts can be actually reliably learned by the proposed architectures, and if not, then which of them? And the second point is, which of these two categories of architectures, fully connected or convolutional, are prospectively more suitable for such tasks? The methodology itself is based on a few background works. I'm mentioning just 3 of them. All of them are using binary or nearly binary visual data, but I'd like to focus on the last one, my past paper, where I preliminarily concluded that fully connected are more suitable than CNN, and I found that for CNN architectures, there was a kind of glass ceiling which limits their performances in such problems. In this paper, I completely reconsidered these conclusions and propose other ones which are, well, more or less on the opposite side. Data sets. Well, actually, nothing spectacular. 12,000 near binary images of very small resolution, each of them containing a certain number of dots from 1 to 6. Images have a mixed polarity, and in order to avoid overfitting problems, which may happen for such small data pieces, The images are not perfectly binary. The values of white and black fluctuate for each individual pixels, and for the actual training and validation, only half of the data set is always used. I mean, randomly selected half, while the other half is used for for testing only, and this is that part for which all the presented results are obtained. And by the way, most recently, I'm trying to use more imbalanced data set corresponding to the number of dots in each image, but this is a different story, which will not be reported today. Now, the concepts themselves. So as I said, the most straightforward numerical concept is the concept of numbers, in this case, numbers from 1 to 6. In other words, understanding from visual data that in this image we have number 6, i.e. 6 objects, number 4, and so on and so on. But we can consider also more complicated concepts like even and odd numbers, small, medium, large, or medium versus all other numbers. And what is important, some of these concepts are what I call compact, and some of them are distributed. So within distributed concepts, you have to jump if you want to move within one category over numbers which are from another category, like in here or over there. While the basic enumeration or these small, medium, and large numbers, these are compact concepts. This distinction is quite important because, as we'll see later, there are significant differences in results for compact and for distributed concepts. Neural architectures are relatively simple, I would say very simple, again, following with some modifications, adaptations, proposals from the past works, and altogether I'm proposing just two variants of fully connected structure and two variants of convolutional one. The fully connected one is, well, as you see, quite straightforward, with the number of outputs corresponding to the number of classes in the concept. For basic counting, there are, of course, 6 categories, 6 classes. For even and odd, there are 2, and so on and so on. And basically, this variant 1 architecture, fully connected, is embedded into variant 2 as the first part, but designed for acquiring, for learning only the basic numbering. And on top of that, there is another fully connected layer which converts these, allegedly learned over here concepts of individual numbers into the actual concept, odd and even numbers or something else. The same idea applies to the CNN architectures. Again, rather straightforward and simple, 2 convolutional layers, and followed by 2 connected layers with the number of outputs the same as it was before. And eventually the variant 2 is the same, embedding variant number 1 and hoping that internally it will learn the numerical skills, the understanding of individual values from 1 to 6, and then another fully connected layer which converts this understanding into the actual concept. And then the experiments. Of course, the first one is basic counting, learning the concept of numbers from 1 to 6 just from images showing corresponding numbers of dots. And it turns out that in this case, no matter which architecture we use, it will be equal or almost equally successful in a sense that it can obtain very high accuracy on the test part of the data set, exceeding 99%. However, if we look at more details of these results, it can be found that CNN are actually far superior. Because if we look at the confusion matrices, we can see that all mistakes which are made are in the area of larger numbers of dots, and that may happen for humans as well. If we look at such images and try to estimate the number of dots without explicit counting, we sometimes can make mistakes. and CNN does the same. Unfortunately, that was the result. For FCNN, the results are rather strange. Sometimes even images with only 2 dots can be incorrectly recognized as images with only, well, recognized as representing the concept of number 1 or number 3, which of course never happens for humans. For those more complex concepts, 2 of them will be discussed with more details, others will be only briefly mentioned. So, learning even versus odd numbers. And it turned out that actually we need to know the numbers themselves in order to know which of them are even and which of them are odd. Because CNN2, that one which has the embedded ability to learn the concept of individual numbers, is the one which can get a relatively high performances approaching 90% for the test data set. All other architectures are stuck at the level of random choice, sometimes a little bit better. I mean, 50 plus accuracy on the testing set. For other concepts, for the second concept, medium numbers versus the others, the same story. CNN2 performs almost flawlessly. I mean, it's learned to perform almost flawlessly, while the other ones, again, are stuck at the level of random choice, which in this case is 2/3, 67%. The same happens basically for all other more complicated concepts, like, for example, 1, 2, many, small, medium, and large numbers. So, and then appears that idea of compact and distributed concepts. It turns out that if the concept is compact, all architectures, including FCNN, can be trained to get a very high accuracy on the training set, on the testing set, exceeding 99% in most cases, or even reaching 100% in some cases. For distributed concepts, when those classes are somehow mixed in terms of their order, then FCNN and in most cases CNN1 are again stuck at the level of random choice, and only CNN2 architecture is able to do it properly, to properly recognize, to properly learn the distributed concepts. For example, and still there are some exceptions, special cases. For example, if we want to train the architectures to learn the concept of numbers which are divisible by 3, so in this case just 3 and 6, of course FCNN fails badly, even below the random choice, but even CNN in the first variant, in other words, CNN, which doesn't know the concept of individual numbers, is able to learn the concept of numbers which are divisible by 3. So this is one of those special cases which require special explanations in the future. But generally, CNN2 is the one which can learn all such concepts, no matter what concepts you propose. And finally, it's time for some summary. But in this summary, first, I would like to discuss the explainability issues, because this is another interesting story. What I found that even if fully connected and convolutional architectures have similar performances, similarly high performances, the internal structure and the abilities to explain this structure, these values, are very different for fully connected and CNN architectures. In other words, for FCNN, we might have some matrices of weights, maybe some specific features near 0 columns or something like that. But if we switch to another concept, which is very similar, and the results should be correspondingly very similar, there is no regularity, there is no repeatability, the results, the weights are completely different, and there is no way we can somehow explain the meaning, explain the significance of some specific values over there. For CNN architectures, the story is very different. If such a structure is successfully trained to recognize certain numerical concepts, the first convolutional layer, just a reminder, there are two of them, is basically always the same. Out of 16 filters, only one plays active role. The others are just looking like averaging filters, and that role is clearly identification of detection of isolated pixels. And it happens no matter what concepts we are learning, whether the concepts of individual numbers, the concepts of even and odd numbers, the concepts of numbers divisible by 3. These first layer filters are always the same. However, if the architecture is unsuccessfully trained, in other words, it is stuck, for example, at the level of random choice, the errors, if I can say so, are basically at this layer. So again, out of 16 filters, only one seems to play an important role, but it's very different, and it's very difficult to explain what's the purpose, what's the role of that filter. For the second convolutional layer, the story is similar or even better. Out of 256 such filters, only one eventually looks like an active one, and its role is always the same. It's just counting the number of isolated dots which were found at the first convolutional layer. And it means that if there are some unsuccessful trainings, and in other words, the structure is not able to recognize, to learn certain concepts, the errors are, or the failures are at the first convolutional layer, because the remaining parts are usually very similar, especially in terms of those filters. So, and then after a little bit longer part of summary, then the final conclusion. So basically, 3 conclusions can be identified from my, of course, limited scale works. The first one is that if you are talking about simple concepts of numbers, learning those concepts from visual data, both FCNN and CNN architectures, of course, within the structures I've been using, can learn such concepts almost flawlessly. For more complicated concepts, everything depends on whether the concept is compact or distributed. For compact concepts, both FCNN and CNN can learn. For distributed, basically, it's only CNN in the second variant, which includes the understanding of individual numbers. Sometimes CNN1, but it's always only CNN which can learn such concepts. And even if both architectures can achieve similar performances, generally only CNN have the internal structure which can be explained, which can be understood, which can be related to the neurocognitive, neurological foundations of counting and number understanding. So basically, that's it. Thank you very much. And if you have any questions and or comments, and if we have time for that, I'd be happy to try to answer them. Thank you.
Thank you, Professor, for a very interesting presentation. I think we are a little bit running out of time.
Yeah, that's what I mentioned.
We got at the beginning, just my short comment, the presented results, some conclusions are really interesting and surprising. That's very interesting research. Thank you one more time, Professor.